today I will start something new. Today for the next few lectures we shall be considering piecewise constant potentials. So these are potentials which over a finite range of x may be treated are constant over a finite range of x, and then the constant value of the potential changes. So let me give you an example of a piecewise constant potential and why they are useful in physics. For example, the nuclear interaction is known to be very strong at small scales, at very small scales. Inside the nucleus they are very strong, but at large scales they are very weak, they don't act at all. Okay, so it is the nuclear potential as a function of, let us say, the position, or we can drop this function of the distance from the center of the nuclei, or the distance between the two particles, say a proton, two neutrons for example. The nuclear interaction is something like this. It goes to 0, it becomes constant. So it is, the potential varies very rapidly over here, so there is a large force in these at some very small scales, and then the potential has no effect at large scales. So such a potential, now these nuclear forces are not, there is no exact form for these nuclear potentials known at small scales. So one has to use some approximate forms for these potentials if you want to do some analytic solution, and the simplest possible kind of thing is to look at it like this. There are more sophisticated models for these potentials, for the potential between two nuclear particles, not two nuclear particles. For example, say a proton and a neutron at very small scales. In addition to the electromagnetic interaction, there will be some nuclear interaction which causes them to get bound. For example, in a deuterium atom there is one proton and one neutron. So what keeps it bound? There is some nuclear force, and that force falls off very fast if you go to large distances. So for many purposes you can model the force as a potential which has a constant low value, constant negative value for some very small length scale, and then once you cross that length scale the potential disappears, it becomes 0. So this is what is a piecewise constant potential, one example of a piecewise constant potential. So this is a nuclear force, nuclear interaction. Another example, so let me give you one more example of a piecewise constant potential where it is useful. Let us consider an atom. Inside let's consider a solid. Inside a solid you have these, say a metal. So in a metal the inside a solid piece of metal, the outermost electrons are free to move around in the metal, leaving behind some positive part. So inside the metal you have these positive ions, metal ions, bound together in a 3-dimensional lattice. Here I have just drawn a 1-dimensional, so it could be a very large lattice, a 1-dimensional picture. And the potential, so whenever the electron is somewhere near this ion, it feels an attractive potential, and then this potential falls off as you go further away. Again it feels another attractive potential here. So this can be usefully modeled as the following kind of potential. And the properties of the electron in a solid, in a metal for example, this kind of a model is true in many kinds of solids, and the properties of an electron can be understood in terms of this kind of a potential. This is a very useful model for studying the electron. It gives rise to the band structure of the electron inside a solid. So this is another application of a piecewise constant potential. This is inside a solid. So with this motivation for the study of piecewise constant potentials, let us now go on to a few examples of piecewise constant potentials. So the simplest situation is what is known as an infinite potential well. Infinite potential well. So what is the infinite potential well? It is a situation where a particle, 1D, so we are doing one dimensional. We are still restricting ourselves to one dimensional problems. So the situation is as follows. There is a particle free to move along the x-axis, and there is a potential. The potential is such that at x less than 0, the potential is infinite. So I have an infinite potential on this side. So the potential, this is V, this is x. The potential is infinite over here, so this is infinite over here. The potential is 0 for some distance a, and then again it is infinite over here. So let me put this in a different color. So the potential suddenly jumps up to infinity at x equal to 0 and x equal to a, and the potential has the value 0 in between. So this is what is called an infinite potential well. It is like a well because this is the bottom of the well and these are the two sides of a well. So classically the motion of a particle inside this is very simple. If I had a ball, for example, moving inside, the ball would move in, suppose the ball were initially moving in this direction, it would proceed like this. It would hit this wall of the well over here because there is an infinite potential there. It would bounce back, come and hit here because there is an infinite force which will act on it. It will just keep on bouncing between these two. Okay, so there is the ball will just bounce between these two ends. Now let us study what happens to this problem in quantum mechanics. So in quantum mechanics, we can study the problem. So in order to study the problem, we have to consider the three regions separately. Region 1, okay, the regions where there is a finite potential and the regions where there is an infinite potential. So let me write down the Schrodinger equation first. So let me write down the Schrodinger equation over here. So the Schrodinger equation is minus h cross square by 2m d by d x square. We are looking at the stationary states because this is a time independent potential. The time evolution, as you know, is quite simple, so we will not bother with it. So the Schrodinger equation is minus h cross square by 2m d by dx square psi plus v psi, v is a constant now, is equal to E psi. Now in the regions to the left and to the right, V is infinite. If V is infinite, the only solution that you have is psi equal to 0. You cannot, the wave function cannot be finite in this part and this part. You cannot have a finite solution because if the wave function is finite, then the derivative, second derivative has to be infinite, right? Such a solution doesn't exist. So for x less than 0 or x greater than a, psi x is equal to 0, and the solution for, so we have to only be concerned with the solution in the region x going from 0 to a. So in this region the solution is quite simple. So let me write down the equation again in a different way. So in this region the equation just becomes d square d x square psi x is equal to so I have v is 0 anyway, so I have minus 2 m e by h cross square psi. And the solutions for these for this particular equation, this is for x going from greater than 0 and a. This is actually in between, in this range. Now the solutions of this equation are very easy to write down. So let me write down the solutions. So the solutions are of this kind: psi x is equal to a cos kx plus b sin kx. You can very easily see that this is a solution of this equation, because whenever if you plug in cos x, it differentiate it twice, you get back the same function multiplied by a constant number, and the number k squared. So if you put this in here and differentiate twice, you get k square outside. So k square should be equal to 2m e by h cross square, or k is equal to square root of 2m e by h cross square. H cross. Okay, so these are the two possible solutions. Now let us also look at the boundary conditions which have to be applied to in this equation. So what are the boundary conditions that have to be applied? Now the boundary conditions that have to be applied are as follows. The wave function should be continuous at the two regions where the potential suddenly shoots up at the boundaries, because you want to take the first derivative and the second derivative, because the Schrodinger equation involves the second derivative. So in order for this equation to be applicable, we want the second derivative to exist here, which means that the first derivative should, if the first derivative is continuous, then we get a finite second derivative, and so the function itself and its first derivative should be continuous across the boundaries, both at the left and at the right. Okay, so we have to impose the boundary condition that psi at 0 is equal to 0, psi prime at 0. Okay, now in this case you cannot actually the derivative. Okay, let us in this case we cannot apply this, the fact that the first derivative is 0. So we have to just impose the boundary conditions that psi a is equal to 0. In this situation, at the boundary the potential is actually going to infinite, right? So this is in the 0 to a. At the boundary the potential jumps to infinite. Here also it jumps to infinite. Now if the potential jumps to infinite, then the second derivative here could also be infinite, and then this could just cancel out, right? So you don't require the first derivative to be continuous in this case, because if the first derivative has a discontinuity, then the second derivative will become infinite because of that, and that can be adjusted, that is acceptable because the potential itself becomes infinite. Okay, so the boundary conditions for this problem where the potential suddenly jumps to infinity is that psi should disappear at a x equal to 0 and x equal to a. So what does this impose? This imposes the fact that the cos kx solution is ruled out, because cos kx does not disappear at x equal to 0. So this is ruled out, which tells us that a is equal to 0. In addition, the fact that it has to disappear at x equal to 0, that this sine kx, so it has to disappear at x equal to 0, that is sine ka is equal to 0. This implies this, which implies in turn, so this implies this, which in turn implies that Ka is equal to n pi, where n could be 1, 2, 3, plus minus 1, 2, 3, 4, etc. So for any integer value of n, the sine Ka will disappear. If k is 0, then the wave function itself becomes 0, which is not what we want. We want the wave function, we don't want the wave function to totally disappear everywhere, right? So n can, so the condition which the boundary conditions impose is that the number k over here has to satisfy the relation that k into a is equal to n pi. So what does this imply for the energy? This implies that n pi squared should be equal to 2 m e by h cross square. So we find that the energy spectrum is discrete. The energy spectrum can be enumerated by the integers, or and there are discrete energy levels corresponding to different integers, and the energy levels are given by the following. So the energy level corresponding to an integer n is h cross square pi square into n square by 2 m. So these are the allowed, where n could be equal to plus minus 1, plus minus 2, etc. So what are the energy levels of a particle in a infinite potential well? The energy levels of particle in an infinite potential well are given, can be enumerated by an integer n, which could take values plus minus 1, 2, 3, 4, etc. The minus sign doesn't make a difference here. And we can actually drop the minus sign because it doesn't matter at all. We shall see that it doesn't matter. So I don't have to bother with the minus sign. There should be an a square, that's right. So this is equal to, right, n pi by a. So this is by a squared, right. So these are the energy levels. H cross square, pi square, n square by 2m a squared, right. K is equal to n pi by a, and which is equal to 2m e by h cross squared, right. So these are the energy levels. So let me now plot the energy levels as a function of n. If I plot the energy levels as a function of n, so this is the energy, which is what I call the spectrum, if you remember. So n equal to 1, and then n equal to 2, the energy level will be somewhere here, let us say. N equal to 3, it will be, the spacing will keep on increasing as I go to larger and larger values of n, because the energy is now proportional to n squared. Compare this with a simple harmonic oscillator where the energy levels were equally spaced. For a particle inside an infinite potential well, we again have a discrete spectrum, but now the energy levels, the spacing between the energy levels is proportional to n squared. So the distance between two energy levels keeps on increasing as we go to larger and larger values of n. So there will be different energy levels, and the spacing keeps on increasing as you go to, this is n equal to 4, etc. Okay. And it keeps on, so there is, it increases. Okay, so this is the spectrum. and there is an infinite, there is no upper limit, so it can just keep on increasing. What are the corresponding wave functions? Let me also put that down. So we found that k has to be equal to n pi by a. So the wave functions psi n x are equal to some a, let us use b, sticking to our convention, b n sine, and k was n pi by a, so I have n pi by a into x. So these are the eigenfunctions corresponding to the different energy levels which are enumerated by n for a particle in an infinite potential well. As you can see that plus minus n, if I choose n to be plus 1 or minus 1, it doesn't matter because that can be absorbed into this coefficient b over here. Multiplying a function by a number doesn't change the wave function, just can be absorbed into this coefficient. The coefficient b of n can be fixed by the normalization condition, which is psi nx square minus infinity to minus 0, no, this from 0 to a, because at beyond that it is 0 anyway, dx is equal to 1. This fixes bn, okay. So now let me draw a few of the wave functions. So if this is psi, this is 0, this is a, n equal to 1, let us look at n equal to 1. N equal to 1, it is just this, this is n equal to 1. N equal to 2 will be, let me just draw it on a different scale. Okay, so this is n equal to 2. Okay, this is this is just the next harmonic. N equal to 3 will have, so n equal to 2 has got one node. The ground state, which corresponds to n equal to 1, has no nodes. It has no intersections with the x-axis. N equal to 2 crosses the x-axis once. N equal to 3 will cross it 2 times, and so forth. So by looking at the wave function, you can directly tell whether it is the ground state, the first excited state, which is n equal to 2, the second excited state, which is n equal to 3, etc. Okay. So the different wave functions can be easily plotted. These are the different wave functions. And we have now got everything about the stationary states or the eigenfunctions of the particle in a potential well. Now, suppose I am given the initial wave function, which could be anything arbitrary. So I am given that the particle, so this is the x-axis, this is psi, this is 0, this is a. So I am given the fact, suppose I have a problem where I am given the fact that the wave function initially is some arbitrary function, and this function has to obviously disappear at x equal to 0 and x equal to a. So given any psi x 0, we can expand this. This is the standard Fourier expansion. So any function in the range 0 to a can be expanded in terms as a Fourier series with n going from, so there will be a constant, so there will be some constant, let us say c naught, plus n going from 1 to infinity cn psi n x. But the psi n x are just the sine functions, right? And we know from the Fourier series, our knowledge of Fourier series, that any function which satisfies certain conditions within the range 0 to a can be expanded in a Fourier series like this. So we see again that the wave functions do indeed form a complete set of functions wherein you can expand any arbitrary function in terms of these functions. Not only that, we also know that the different signs of these, we also know that these functions sin n pi a by x, they satisfy the condition that if I take n and m, two different functions, and multiply them and integrate them from 0 to a, unless n and m are the same, these integrals are 0. And only if they are the same do I get some number. And we have normalized these wave functions, so the wave functions are also normal, orthonormal. So that is psi nx, psi mx, psi n star psi m dx 0 to a is equal to delta nm. These are standard, this is very easy to verify. You have to just put in psi n and psi m x and do the integrals, right, which are just sine functions. And we know that this is true because this is how you work out the coefficients in the Fourier expansion. Okay, so these wave functions we see that they form a complete orthonormal basis. So these form what is known as a complete orthonormal basis. Okay. So if you now want to look at the time evolution of any arbitrary wave function, you can just multiply each of these with the corresponding phase, which is a function of time, and then add it up and do all kinds of things which we have already discussed in the context of the simple harmonic oscillator. So I will now stop with the infinite potential well over here. The infinite potential well is a very useful model in many situations. Suppose you want to model an electron or a particle in a room, for example, or in some large box, then you can treat it for many purposes as an infinite potential well. Even an electron moving inside a metal or inside a solid for certain purposes, when you don't want to bother about the atomic structure inside, you can model as an infinite potential well or as a finite potential well, because the energy which has to be given to the electron to remove it from the solid itself is pretty large compared to the energies involved when it moves inside. So you can model that also as a particle in an infinite potential well. So this is a very useful model which you can apply in many situations. Okay, and we learned from this model that for a particle in such a potential well, the energy spectrum is discrete. The energy spacing increases as you go to larger and larger values of n, and we also saw what the eigenfunctions are. Okay. So now we move on to something else, in the same topic, that is piecewise constant potential wells. So now we go on to something else. In all problems involving piecewise constant potentials, you will encounter such boundaries where the value of the potential will change. The potential, as I have told you, is piecewise constant. So when it changes from one constant value to another, there will be boundaries. So we want to now see what are the conditions, boundary conditions to be imposed whenever we encounter the potential suddenly jumping, and how to go about dealing with these. Okay, so before going to that, let us work out the form of the wave function in different situations in a constant potential. So let us work out the eigenfunction, the wave function in a constant potential, and then we shall apply the boundary condition with the value of the potential changing. So in a constant potential, the Schrodinger equation is very simple. Let us just look at the Schrodinger equation once, and then we can write down the Schrodinger equation directly. So this is the Schrodinger equation. So in a V is a constant, so we can take V onto that side, take all these factors onto the right hand side, take the minus sign over there. So the wave function which we have is d square dx square psi x is equal to, and I have 2m by h cross squared. Let me put the minus sign here also, and then I have E minus V. And if I define this whole thing to be k squared, like we have done in the situation which we considered just earlier where V was 0, then this is equal to minus k square, this is a psi over here, minus k square psi, where k is equal to 2m E minus V by h cross square. So if E is greater than V, if the energy of the particle is greater than the potential, so I have a potential over here in some, so this is V, let me draw it here, this is my x-axis, I am plotting V over here, this is some constant value V of the V over here, let us put it as, okay, so V, this is the constant value of V, and my energy is here. In such a situation, the solution is very simple. The equation can be reduced to this d square psi by dx square is equal to minus k square psi, where k is this square root of 2m E minus V by h cross square. Here E minus V is positive. And the solutions of this equation are quite simple to write down. So the solutions are psi x is equal to a e to the power I kx plus b e to the power minus I kx. So this is if E is greater than V. Now next let us look at a situation where E is less than V. Classically, a particle cannot be in a potential, particle with an energy E, you won't find it in a region where the potential is more than the energy of the particle, right? Because classically the kinetic energy plus the potential energy is equal to the total energy. The kinetic energy has to necessarily be positive because it is half m v squared, and v is a real quantity, so kinetic energy is necessarily greater than 0, which implies that classically if v is greater than E, you will not find the particle there in that position. Not find the particle. So if this is the potential, so the potential is something like this, and the particle has, this is V, and the particle has energy E, the particle will move within this range classically. The particle will move between this range. You will not find it in a region where E is less than V. But in quantum mechanics, we have to look for solutions of this equation even when E is less than V. If E is less than V, then this equation, the same equation we write it in this way. D square x dx square psi now becomes equal to some rho square psi, where this is positive. Okay, and rho is equal to square root of 2m v minus e by h cross square. So the only difference is that we had a minus k squared, now we have plus rho squared, and the minus sign has gone into this over here. Okay, now we have v minus e instead of e minus v. And the solution of this equation is also very simple. It is equal to a e to the power rho x plus b e to the power minus rho x. So if the energy, so there is a qualitative difference in the form of the wave function depending on whether the energy is greater than the potential or less than the potential. If E is greater than V, then the wave function behaves like this, psi versus x, it oscillates, right? E to the power ikx is an oscillating function. The amplitude remains the same, doesn't die down. If if the energy is less than V, that is in the regions which are classically forbidden. So if you look at the wave function in this region over here, where the energy, this is the energy, is greater than the potential, the wave function will have an oscillatory behavior. In the region which is classically forbidden, that is where the energy is less than the potential, the wave function will die down or has an exponential behavior. So the wave function will either decay exponentially or it will grow exponentially. And you have to use appropriate boundary conditions to fix which of these you are going to have. So there is a major qualitative difference in the nature of the wave function in the two regions, one which is classically allowed. This is classically allowed for a particle. This is not allowed classically. The wave functions e to the power ikx and e to the power minus ikx can just go over to e to the power, so the wave function e to the power ikx will go over to e to the power rho x if I have k going to minus I rho. So in all of the analysis now which I am going to present, I am going to use e to the power ikx, and you can easily convert it to a situation where I have an exponential kind of wave function by just setting k equal to minus I rho. Similarly, e to the power minus ikx will go to e to the power minus rho x. Now the situation we want to consider is as follows. We want to consider a situation where we have two regions, region 1 and region 2, and the value of the potential changes abruptly across these two regions. So I have a situation where this is my x-axis, this is the potential V, this is x. At some value of x equal to a, the potential jumps from V1 to V2. So the potential is like this, and the potential suddenly jumps to this. This is V1 and this is V2. And I want to see how are the wave functions over here, which I shall call say psi 1, and psi 2. So, the wave function here is psi 1, the wave function here is psi 2. I want to see how these wave functions are related. Now, as I already told you, the wave function must be continuous across this boundary at x equal to a. In addition, the first derivative must be continuous. Here the potential is finite both over on the left and as well as on the right. So, the first derivative also must be continuous across the boundary. So, not only must the wave function be equal at this the left hand, the wave psi 1. So, the boundary conditions are psi 1 at the point A should be equal to psi 2 at the point A, and psi 1 prime at the point A should be equal to psi 2 prime at the point A. The derivative should also match. Now, on the left hand side, the wave function psi 1 x can be written as some a1 into e to the power I k1 x plus b1 e to the power minus I k1 x, where k1 we can calculate using the potential V1. So the wave function is just if the energy doesn't matter, okay, the energy is greater than the potential, then the wave function we have seen is this, where k is related to the potential in this way. So on the left hand side we have a different value of k from the right hand side, and the value of k on the left hand side I am calling k1, on the right hand side I am calling k2 in the region V2. So over here I have psi 1 is this, and on the right hand side I write psi 2x to be equal to a2 e to the power I k2x plus b2 e to the power minus I k2x. Now let us apply these two boundary conditions to these wave functions. So the first boundary condition, that the value of psi should match, is very easy to implement. So the first boundary condition tells us that a1 e to the power I k1a plus b1 e to the power minus I k1a is equal to a2 e to the power I k2a plus b2 e to the power minus I k2a. So this is the first relation that we have, and this comes from the fact that the wave function should match at the boundary. Now let us also see what happens when we match the derivatives. The derivative of psi 1x gives a factor of ik over here, and it gives a factor of minus ik over here. Similarly, the derivative of psi 2 will give a factor of ik2 and minus ik2. So the derivative of this function will have a overall ik1 outside, and there will be a minus sign over here. The derivative of this will have an overall ik2 outside, and it will have a minus sign over here. So if I match the two derivatives, then the relation which I get is that I k1, then I have a1 e to the power I k1a minus b1 e to the power minus I k1a is equal to I k2 a2 e to the power I k2a minus b2 e to the power minus I K2A. So the boundary conditions give us these relations between the coefficients A1, B1 and A2, B2. So we see that these coefficients are not independent. If I fix the wave function psi1 over here in this region, then the boundary conditions, there are two boundary conditions and there are two unknown coefficients in psi2. So these two boundary conditions will fix the values of A2 and B2 and finally fix psi2 on the right hand side. So basically what we have is a relation between A2, B2 in terms of A1 and B1. So let us work out this relation between A2, B2 and A1, B1. So in order to work out this relation, what we have to do is just take this over here. So what it gives us is, okay, we want to express A2 and B2 in terms of A1 and B1. So let us see how to go about doing it. Okay, so let us divide throughout by I K2. If we divide throughout by I K2, then this will become K1 by K2. And then if we add the two of these, what do we get? So we are going to add the two equations after dividing the second one by I K2. So if I add these two equations, the right hand side, let me write down that first. So the right hand, let me write down the right hand side first. So the right hand side will give me 2 into A2, 2 into A2 into e to the power of I K2A. So I have divided this by K2, I K2, so this has gone, and then I have added these two equations. So I have 2 into this first term, the second term cancels out. I am looking at this part here and here. The second terms cancel out, and these two terms get added up. So this is equal to, so here I have 1, and I have divided this whole equation by I K2, so I get 1 plus K1 by K2 into A1 e to the power I K1A plus I get 1 minus K1 by K2 e to the power I K2A into B1. So finally we have obtained A2 in terms of A1 and B1. So let me write down the relation for A2 in terms of A1 and B1. So A2 is equal to half 1 plus K1 by K2 A1 e to the power I K1 minus K2A plus half 1 minus K1 by K2 e to the power this term over here should have a minus sign, so there should be a minus sign here, and because B2 appears with a B appears with a minus sign, so what I have over here is minus I K1 plus K2 into A. By using this, putting this back into the original equation, we can also work out what is B2. I will not work it out here. I will leave it for you to work it out, and we shall assume the form for B2 in the next class. So for today I will stop here.